All right, everybody, welcome back. Today we're going to proceed with our parabolic equation solution methods. Today what we're going to go over are some implicit methods, because we ended the last lecture with a discussion about stability analysis, and then we went and showed in the Jupyter notebook how if you chose a time step that was too large with word time central space, you would end up with those sort of out of control oscillations, right? So in the last lecture, were generally the two main topics were the forward time centered space method, where we applied the central difference operator in space and then explicit Euler in time, and we noted that it was an explicit method. And in essence, what it boiled down to was it was a spatial average, or each point in space at a certain time step was a spatial average of neighboring points at the previous time step. At previous time step. Okay, and then we ended the lecture with a discussion of the modified wave number analysis, which may have seemed a little confusing or overwhelming, but the important thing to remember is that you really are just trying to get lambda and perform the same sort of stability analysis that we've been doing so far in this course. So the general workflow is you assume that your solution is some function of time times e to the I kx, and you apply your discretization. And then you will be able to rearrange to the overall form the partial derivative of psi with respect to t is equal to minus alpha k prime squared times psi, and then let lambda be equal to minus alpha k prime squared. And remember, the alpha was the diffusion coefficient in that ODE. Okay, so lambda depends on your discretization scheme and the governing equation. Okay, and then after that you just do your normal stability analysis with lambda. Okay, so let's go ahead and just jump right into it. Like I said, at the end of the last lecture we we showed how if we chose a time step too large, we would get those out of control oscillations, and essentially get garbage for a numerical solution. And some of you might have predicted that the way to deal with that is to use an implicit time stepping method. In fact, I might have even said that in the last lecture, but I don't remember. So what we're going to do right now is backward time centered space, which is exactly what it sounds like. Which is to say that it is implicit Euler and central difference. So let's apply it to the exact same equation that we did before, where we have dt, the partial derivative of the temperature with respect to time, and then we're going to evaluate that using the backward difference time operator at a grid point I and t n plus 1. Okay, and that's going to be equal to alpha times the second derivative of the temperature with respect to space with the central difference operator applied at grid point I and t n plus 1. Okay, so what does this look like? Then we have ti n plus 1 minus t n at grid point I divided by, sorry, that was a little bit too big, divided by delta t is equal to, or approximately equal to, since we're applying a discretization scheme, we should put that in there, alpha times ti minus 1 at time step n plus 1 minus 2 times ti n plus 1 plus ti plus 1 n plus 1, all divided by delta x squared. Okay? And then we can go ahead and rearrange and put all of the tn plus 1 stuff on one side of the equation and all of the tn stuff on the other side of the equation. So what we end up with is the following, where we have, and let's just really quickly, let's let alpha lambda equal alpha delta t over delta x squared as before. Okay? And then what we'll end up with is the following, where we have minus lambda t I minus 1 n plus 1 plus 1 plus 2 lambda times ti n plus 1 plus lambda, or actually minus lambda ti plus 1 n plus 1, and then that on the right hand side is going to be equal to ti n. Okay, so what's happening here? Well, we can actually look at we can look at grid points, for example, to give us a visual idea. So remember how last time we were doing an average of the neighbors and at a given grid point at the previous time step would go and feed into whatever the value is. But then in this case, we're not just averaging up the previous time step values, we're also averaging up like the current time step values. So we have t n plus 1 here, and then tn, so the time axis is going up and down. And then we have, let's say this is like xi, oops. This is xi, this is xi plus 1, and this is xi minus 1. The way it's going to flow here is if we want to solve for the I n plus 1 node value, we need to take its neighbor at the same time step to the left and right that flow in to this overall average, including itself for that matter, and then just the previous time step exactly. Okay, so this is the general kind of flow that's happening for every node, like that. Now, you can see kind of right away that, at a given time step, we don't know what the next time step is going to look like. So we're left with this thing where we're going to have to solve for all of the next time step grid points simultaneously. So you might guess that you're talking about, we're going to have to set up a linear system here. And then invert the matrix, right? So in the interior, aside from the boundary conditions, which we need to kind of handle on their own, we get the following set of equations where, say, for the first interior point, we have lambda t1 at time step n plus 1 plus 1 plus 2 lambda at times t2 at n plus 1 minus lambda at t3 at time step n plus 1 is equal to t2 at time step n. Okay, and then we can, the next line is going to be the same, just with all the grid point values incremented by 1. So like this would be the equation for t3, let's say, if we want to name it by the center node or center grid points. T4 n plus 1 is equal to T3 at time step n. And then you can continue this down for all the equations. And what you're going to end up with is a tridiagonal matrix, right? So here's what that looks like. So we're going to have the first equation is is going to have, there's actually two different ways that we can deal with this. So you can, in general, what you do is you apply the discretization to the boundary condition, and then that will allow you to solve for t0 for the first interior point. So the first line of this matrix is actually going to be for t1, which is not this equation here, right? So let me explain. So I'll start filling out these values and it'll become clear. So I'm starting with 1 plus 2 lambda. The next entry is minus lambda. And then we have 0, and then those entries continue to the right, and then eventually we'll have another 0 over here, and that'll be the end of the first row. The first element of the vector that we're multiplying this matrix by is t1, n plus 1. Okay, so that's the first interior point. Okay, and then we have, excuse me, and then we have, that's going to be equal to, on the other side we have t1 at time step n, so that would be the right hand side of the equation, but we also have minus lambda t naught at n plus 1, right? So what we've done is we've taken the, if we had written this equation here for centered at t1 or at grid point 1, then we would have this over equation here, but we're moving the boundary value into the right hand side, because we have Dirichlet. For this problem we have a Dirichlet boundary condition, which is that t naught and tn are known for all time. Right, so that t naught value is just a constant value. We don't even need to put a superscript on it. So we can happily move t naught at time step n plus 1 over to the right hand side because we know what that value is going to be at time step n plus 1. So if we proceed, then we do minus lambda here, and we have 1 plus 2 lambda, and then another minus lambda, and then a 0, and so on until 0 is to fill that out. Then we'd have 0, minus lambda, 1 plus 2 lambda, minus lambda, 0, and so on. And then those three diagonals continue down the matrix. Okay, and then we'll have a final couple of rows. We're going to have 1 plus 2 lambda, minus lambda here, and then 1 plus 2 lambda here, minus lambda here, minus lambda, 0, 0. These zeros continue down, and we have these zeros continue over that way, and there's a 0 here, and that goes that way. Okay, so hopefully that's not too messy. Then we have t2 here, to n plus 1, at time step n plus 1. That continues down until we have tn minus 1, where we have n interior points, n plus 1. So, or n minus 1 interior points. So basically we're solving for all the interior points simultaneously at each time step. And then this would have t2 at time step n, and that would continue until we had tn minus 2 at time step n, and then the last entry is going to be tn minus 1 at time step n, minus lambda tn at time step n plus 1, because remember that value is fixed. Okay, so this is what the overall tridiagonal matrix setup looks like. Let me make these vertical dashed lines a little bit more clean here. Okay, so that's the overall structure. And the good news is that a tridiagonal matrix is very efficient to solve. So, but unfortunately, it's like when we were solving ODEs, the implicit method requires a costly matrix solve, matrix inversion at every time step. But like I said, the good news is that it's a tridiagonal matrix, which is efficient to invert. It's not like a dense matrix. So another thing to keep in mind, another note that I have here, is that we've only been applying these methods to linear equations. So remember, only linear equations so far. Nonlinear equations require special treatment. So you're not going to end up with a nice big matrix system, right? Because once you apply your discretization, you're going to have nonlinear functions of the grid points present. So this sort of approach is not going to give you a clean results every time. Okay, and then another thing that we may have noted is that, you know, although these two methods are second order in space, they're only first order in time, right? So f forward time centered space and backward time centered space first order in time. So what we're going to do right now is look at a popular method that's higher order in time. Okay, and that method is called Crank-Nicholson. And I can't remember if there's a C or not here. Excuse me. Okay, so this method actually still uses center difference approximations in space, but it uses the trapezoidal method in time, or another, sometimes that's called the leapfrog method, I believe. So this is still centered space, or center difference in space. But trapezoidal in time. Okay, and so the way we label this, because we're dealing with the trapezoidal method, is we say the partial derivative with respect to time with the temperature evaluated using center difference in time, right? At the grid point xi and t n plus 1/2. Okay, so we're imagining that there's some imaginary grid point in between our two actual grid points, and that's the center, and then we're using a center difference operator on the time side. And then on the right hand side, we're also using center difference for the second derivative of the spatial operator, but we're still doing this at, you know, n plus 1/2. This is just some, we'll just call it trapezoidal method, traps labeling. You'll see how it works out when I actually write out these terms. So what we have on the left hand side is center difference in time about this fictitious center point, which is just going to be ti n plus 1 minus ti n over 2 times delta t over 2. So that would be center difference about that fictitious point. It looks a lot like forward difference, but really where you get the difference, or the difference, but the contrast, the word I'm looking for, is what happens on the right hand side. So what we do to represent this t at n plus 1/2 on the right hand side is we just take the average, so we're dividing by 2 here, of the central difference operator applied to to this term at tn plus 1 and tn. So this would be at grid point I and at tn plus 1. And then we're going to add that to the partial derivative with respect to time. Sorry, with respect the second derivative with respect to space at the temperature. We're going to apply the central difference operator to that at grid point I again, but at tn. Okay. So we're averaging the two. And then what you end up with at the end is a tin plus 1 minus tin over delta t is equal to alpha over 2 times ti minus 1 n plus 1 minus 2 ti at time step n plus 1, sorry, not n plus 1, plus ti plus 1 at time step n plus 1, all over delta x over 2, plus the same thing, but all just time step n. So ti minus 1 at n plus, or sorry, minus 2 ti at time step n plus ti plus 1 at time step n divided by delta x squared. Okay? Once again, we're going to let lambda equal the same thing it's equal to before. And then what you end up with is this equation where you have 1 plus lambda times tn plus times ti n plus 1. You're going to have a minus lambda over 2 times t n plus 1 at I minus 1. Yep. Plus, or sorry, another minus right here. Minus lambda over 2 ti plus 1 n plus 1. So that's coming over from these two terms here, here, and here. Okay. Excuse me. And then you leave of course, all the current time step or tn terms on the right hand side. So then you have lambda over 2 ti minus 1 at time step n. Sorry, I'm dropping the parentheses here, but I'll just leave them like that for now. Plus I minus 1. Sorry, 1 minus lambda. I don't know why I said I minus 1. Plus 1 minus lambda times tin. Okay, and then plus lambda over 2 times ti plus 1 at time step n. Sorry, let me just clean this up here. I dropped the parentheses, so I should keep it consistent, at least in this one expression. Okay, so what do we have here? Well, what we have is a two tridiagonal systems on both sides, right? So it's also implicit. Right, we can see from here that we're having to do some sort of matrix solve here. Not everything is at the next time step is written in terms of things at just the previous time step, right? So let's go ahead and see what the overall matrix structure is going to look like. What we'll have is the following. So this time we have 1 plus lambda on the diagonal, and then minus lambda over 2 off the diagonal, then zeros, and then that continues over here. I'll write the second row here, minus lambda over 2, 1 plus lambda, minus lambda over 2. Let me arrange, get this 0 aligned here. Zeros over to here to the end of the matrix. And then we'll go ahead and extend those down a diagonal. Okay, and then the last two rows are going to be what you would expect, 1 plus lambda as the last entry, then a minus lambda over 2 there, then a 1 plus lambda above that, a minus lambda over 2 the end there, and minus lambda over 2 here. We have a 0 and a 0, and those continue over. So essentially zeros, all except for the three diagonals. Okay, and then here we're talking about the interior points, t1 through tn, but at time step n plus 1. That's what our vector that we're multiplying by here. So tn minus 1 times n plus 1. So that's what we're gonna call that is t internal at time step n plus 1, so in vector notation, and then we'll call this matrix just A. Okay, and then that is going to be equal to same type of system on the right hand side, but on the diagonal we have 1 minus lambda, and then off the diagonal we have positive lambda over 2 here, and 1 minus lambda over 2. Those tridiagonal systems continue down that way. We have a 1 minus lambda as the last entry, a lambda over 2 above that, lambda over 2 to the left, and then the matrix on this, the vector on this side of the equation is all the interior points, but at time step n, tn minus 1 at time step n, and then we can call this t interior, the vector, at time step n, and then we'll call this matrix just B, okay? And then we also have this term, this vector here, which will house the depends on your boundary condition, right? So we have, in our case, since we're using Dirichlet boundary conditions, we're just gonna have lambda over 2. Now remember, Dirichlet just means that you're just setting the value at the boundaries for all time. But if you have a different type of boundary condition, which is something that you'll explore in your homework, you put in different value. This sort of extra vector here is going to look different. Okay, so this is Dirichlet boundary condition. And then just to remind you, this whole vector here is known, right, at the current time step. You don't know what the next time step is. Okay, and then as a practical matter, if you want to actually solve this system, you're just going to use just a single line call. So most of the work, and you'll see in the example that we'll go through in a few minutes here, most of the work is setting up the matrices, and then you just have a one-liner where you just say np.linalg.solve, and then you feed it A is like your system matrix. That's the one that you're inverting. Okay, that's the one that's applied to the next time step that you have to invert. But then the right-hand side, instead of just normally you put some sort of B there, like an AX times B, your B vector is going to be B times T at time step N plus lowercase b, and I forgot to label that. That's what this vector is. It's a lowercase b. Excuse me. That's going to be your vector at the next time step, n plus 1. Okay, and you do that every single time step. All right, so that is Craig-Nicholson. Now, the code for this method is going to look like overwhelming and maybe a daunting, but really it's very simple. It's just implicit. It's like a mix of forward time central space and backward time central space. You just have a matrix on both sides. So like, just get this picture in your head of these two, this matrix equation on the screen right now when you're thinking Craig-Nicholson, and that'll kind of guide your thinking on for actually deploying the method. Okay. So before we go over to the numerical solutions, to give you show you some plots and stuff like that, right? Let's talk for a moment about higher dimensions, right? So here we had one time dimension and one space dimension, right? For these parabolic equations. So the question becomes, what if you have more spatial dimensions, right? So by higher dimensions, I mean more spatial dimensions. So we still have just that one single time-like coordinate, but we might have like x and y, okay? Long story short is that the extension to higher dimensions pretty much works like you would guess it would, and I know that might sound a little trite, but once I start kind of explaining this to you and putting it forward, you'll be like, oh, okay, yeah, that makes sense. Assuming everything up to this point has made sense, which may or may not. So let's go. This time we're going to do the same type of equation, but we're just going to have x and y, and we'll be solving for phi. So we have the Laplacian in 2 dimensions on the right-hand side this time. Right, and we'll say our domain is just between 0 and 1 for both x and y. Okay, sorry, let me make that a little bit cleaner. Less than or equal to 1. Okay, and then what do our boundary conditions look like? Well, we have the following, where we have the derivative of phi with respect to y evaluated at x0 t, so at the y equals 0 boundary, the left-hand side boundary is equal to 0. And the derivative of phi with respect to y at the y equals 1 boundary is equal to 0. So in other words, the function has to sort of be flat at the top and bottom boundaries of the equation, or sorry, of the domain. And then we have that the derivative in the x direction at the right hand side at x equals 1, y t has to be equal to 0. And then we're going to define a piecewise Dirichlet style boundary condition of phi 0, 0, y. This is 0.25. So a region of y here, the first quarter of y, near the bottom of the domain, and t is going to be equal to 0. And then we have phi 0, and then we'll say y between 0.25 and 0.75. In that region for all time is going to be pinned at 1. And then phi at 0 for y greater than 0.275. I should make one of these non-inclusive here. That's why we have a bit of a contradiction. Y greater than 0.75, we're going to have be equal to 0 again, right? So there's a boundary. So let me sort of draw what I mean here. So we have this 2D plane, x and y, and then it ranges between 0 and 1. So we have this domain here. We know that d phi dy, is going to be equal to 0 here. D phi dy on the bottom is going to be equal to 0. D phi dx is equal to 0 over here. Okay, and then there's this region between 0.25 and 0.75 right here, where phi is held equal to 1. Okay, so that's what the domain looks like given these boundary conditions. Okay, so then let's just use forward time central space, right? So if we want to use that, then keep in mind that phi is a function of xi, y, j. So now we're going to have to introduce another spatial index, and then t. And here we'll just do n+1 because that's what will happen on the left-hand side here for 4 times central space. So that thing, that what I just wrote down there, ends up, you can write that as phi I comma j at time step n+1, right? We have minus phi I j at time step n divided by delta t plus, and then this is where we just apply the central difference operators, but one is in x and one is in y. So I shouldn't say plus here, I should say equals d times the quantity phi I minus 1 times j at time step n minus 2 phi I j at time step n plus phi I plus 1 time step j, or sorry, grid point j at time step n, delta x squared plus d times the quantity I. So this is that we're solving this centered at point xi yj, or point ij. Then we have ij minus 1 at time step n, minus 2 times phi I comma j at time step n plus phi I comma j plus 1 at time step n, all divided by delta y squared now. Okay, so that's the partial derivative operator applied in both. Now let's, for simplicity, this is often the case anyways if we're solving a problem like this, we're going to assume that delta x is equal to delta y. Okay, and then we'll let lambda be equal to the same sort of type of value. This time we don't have alpha, we have d, but we'll still just let it be equal to d delta t over delta x squared. Then what we end up with is the following, where phi ij at time step n+1 is equal to lambda times phi I minus 1 comma j at time step n plus phi I plus 1 comma j at time step n plus phi I comma j minus 1 at time step n plus phi at I comma j plus 1 at time step n. So that's that whole quantity, plus 1 minus 4 lambda times phi ij at the previous time step. Okay? And this is true for all the interior points. So for interior points, because we wouldn't be able to apply the differencing operator on the boundaries, of course, right? Okay, so that's it's just an explicit method. You're just averaging all the neighbors, right? In both x and y now, to get the next time step. So the question becomes, like, how do we deal with these boundary conditions, right? Okay, well, first off, the Dirichlet boundary conditions. Is easy, right? Because that's just where we say that phi 0 j, for any y value at time step n is known for all. That's what the upside down a means. It's for all j and n, right? So this is just we already know that. That one just sets the value. For the Neumann boundary conditions, we actually use central order finite difference and backward difference formulae to maintain second order accuracy in space. So what do I mean by that is we do this. So for Neumann, use second order forward difference and backward difference. And what that looks like is the following, right? So we need to set the derivative of phi with respect to y at every point where j is equal to 0 for an arbitrary time step. We'll just say n+1 here. That needs to be equal to 0. And so we're going to approximate that with a second order forward differencing formula, which in this case is going to be -3 times phi I comma 0 at n+1 plus 4 phi I comma 1 at n+1 minus phi I comma 2 at n+1, all divided by 2 delta x. Okay, that's going to be equal to 0. So this is sort of this forms one of our constraint equations given our boundary condition. Okay, and then we'll just go ahead and write this out for the other two boundary conditions. We have d phi dy, but this time we want to do at I j equals n y, so our number of points in y. And again, we'll just choose an arbitrary time step here. So we have now since we're doing a backward difference in space, okay, then the signs will flip. So we have phi I at grid point ny minus 2 at time step n+1 minus 4 phi I comma ny minus 1 at time step n+1 plus 3 phi I comma ny at time step n+1. And I know that we haven't seen these differencing formulas yet, but this is like you could easily derive these using the Taylor table approach that we covered earlier in the class, right? Then we have the last boundary condition, which was the right-hand side boundary condition. We'll do this one at n+1 as well, but this is I equals nx now. xj, and that thing is approximately equal to the following. It's literally the same exact general form as the equation above it, but we're changing the x indices now. So nx minus 2 j at time step n+1 minus 4 phi nx minus 1 at j n+1 plus 3 phi nx j, so for all j at n+1, all divided by 2 delta x equals 0. Okay, and so you might notice that there are interior points inside these boundary condition values, right? Or inside these boundary condition constraints functions, your equations. So what you do is that you find these interior point values using the update rule above. So the first thing you do, at any time step, you have all the boundary values and everything, right? So then you use the update rule above to update all the interior points, and then you take those interior point values and you use them here to update the boundary point values as well, to obtain boundary values. Because remember, even though the left-hand side of the equation, or the x equals 0, that whole boundary, we know what that value is for all time, but the other ones is just the derivative that's constrained. So those values are going to change. They're going to shift upwards throughout time. I'll actually show you an animation of that in a minute, okay? So, to use implicit methods, some tricks are necessary for the spatial part when you're going to 2 dimensions, but we'll cover that next time, okay? For now, I want to talk a little bit about stability. In this higher dimensional context. So we still use modified wave number analysis. But this time, we set phi equal to, again, psi of t, but we set it equal to e to the I kx x times e to the I ky and y. Okay, so we're assuming that, Fourier-like dependence, complex exponential dependence in both directions, in a simple way. Okay, so what you'll end up with once you carry out the analysis is you'll have d psi dt is equal to d times minus kx prime squared times psi minus ky prime squared times psi. And then since delta x is equal to delta y in this case, you get the following, where d psi dt is equal to minus 2d over delta x squared times 1 minus cosine of kx delta x minus 2d over delta x squared times 1 minus cosine of ky delta x. That whole thing multiplied by psi. Okay, so it's really just kind of like it's just mixing or not mixing, but doubling the same thing that we found for the 1D case. Remember that for explicit Euler, we need that delta t is less than or equal to 2 over the magnitude of lambda. And then the worst case, kx and ky, which is what we need to choose to make our stability criterion, lead to the following stability criterion. So lead to delta t must be less than or equal to delta x squared over 4d. So we still get that for forward time-centered space, that stability criterion that requires the time step to scale with the spatial grid size squared to maintain stability. Okay, so now what we're going to do is we're going to move over to the Jupyter notebook and have some interesting things to share with you. So let's go ahead over there. All right, so let's see here. We want to use this kernel. Okay, and then let's see. I think the way I'm starting this here is I'm just going ahead and running what we found in the previous lecture, right? So remember that in the previous lecture we were dealing with we used the forward time central space method to calculate the solution to that heat equation problem for the temperature in the rod. And we showed how when we chose a time step that was too large, right, you got this behavior, these unstable oscillations that gave you non-physical values, right? But if we did a dt equal to 0.1 with 2,000 time steps, we would get this nice behavior. But if we just set our dt to some value that was just twice as large, to 0.2, then we would get this total nonsense, right, with the instability propagating into the domain. So what we're going to do now is we're going to implement a backward time-centered space to show how even with a much larger time step, we can get a stable solution. Okay? So let's go ahead and go through here building these matrices. So we have our domain length, our dt, and then for this time, let's see, and I did that for Crank Nicholson. I should probably use a time step that's larger to make the point, right? So let's just use the same unstable time step that we use here, show that we get a stable solution. Okay. All right. So then we're just doing a parameter input, right? T implicit, like X implicit, boundary conditions, Dirichlet. And so now comes the time to calculate our things. So remember that we defined our lambda. I'm gonna have to snooze cursor tab again. So let me do that after I finish writing this term here. So this is just literally transcribing from the lecture. Okay, we're back, and then and so we're taking this lambda value. We have our number of interior points, and yes, now it's time to build our matrix. So what we can do is we can build the matrix. I'm going to show you one way of building a matrix here, okay? So you can do it through loops. This is going to be a little bit more of a fancy way of doing it. So what I'm going to do now, we know that along the main diagonal, it's the same value every single time. It's just going to be 1 plus 2 times lambda implicit, right? Okay, that's the value. And so what I'm going to do is I'm going to multiply that by a vector generated with ones, numpy.ones, with n interior number of entries. Okay, so I'm literally specifying all the main diagonal values at once, and then the off diagonal elements are also all identical. So the off diagonal is equal to, it's just negative lambda implicit, right? Okay, and then now I'm going to multiply that also by np.ones over the interior points, but the diagonals, the off diagonal elements have one less entry, right? They're have one less value over the extent, and then we can construct the matrix A by adding three matrices together. So there's this function called np.diag, right? And what this does is it creates a diagonal matrix given a diagonal that you feed to it. So I'm going to do main diag, right? But the second argument of this function tells you whether, if it's 0, then it's giving you it's going to place those diagonal entries right along the main diagonal, right? But if that value is 1, it's going to place it above the main diagonal in the matrix. So I'm going to add to this plus np.diag of our off diagonal elements, right? But I'm going to place that on 1. Okay, so the line above the main diagonal, and then I'm going to do the same thing again with the off diagonal elements again, but just below the main diagonal, so -1. Okay, so that is the placement, the creation of the implicit matrix A. Then we're going to do our enough time steps to reach t equals 200 for the demonstration. It'll be fewer than 2,000 steps because we're trying to show how it's stable here. Then we're going to store the initial condition, snapshots every time step, every 10 time units. So just for plotting, stuff like that, right? And then we go ahead and get to the loop, right? So the right-hand side is just the interior values of the last time step, t old. So we'll do t old from 1 to -1, right? And then we're also going to do a copy here so that we don't end up doing any sort of weird in-place editing. Okay? And then we have lambda implicit times t old at time step 0, right? This is we're putting in our boundary condition values. So we're just adding to the first and last elements of the right-hand side this value that we know from the Dirichlet boundary conditions. T old had -1, so the last element of t old. Okay, and then we just solve the tridiagonal system. np.linalg.solve a comma right hand side. Right, it's really that simple. And then our t implicit new is going to be t interior new. Our t implicit new from 1 to -1. Right, that we just calculated. We're going to place that into the solution vector. And then the boundary conditions, we don't even need to do this because we can just leave them what they were before. But just for transparency's sake, so you can see what's going on here, we're just going to enforce the boundary conditions like I said here. But in reality, we actually don't need to do that because we can just leave them the same values that they were before. Okay? Then we go ahead and check and see if it's time to store a snapshot and continue. Okay, and so let's convert the stored solutions to an umpire array for plotting. Then we'll go ahead and plot the solutions, which we can do here. And let's see, where do we get an error here? Let me see if I remove these guys. Maybe that's part of the issue. It was the commas. That's my bad here. So I don't know why I placed these commas here. This is not these commas don't need to be there. That was the mistake. Just a syntax mistake. Okay, and then we get this, and look, so we're having, half as many steps and a perfectly well-behaved solution. All right. And then what I'm doing next is I did wanted to implement Craig Nicholson one time for you guys. You can kind of go through this. I'm not going to actually write out any code for the Craig Nicholson side, but the main idea is you're just calculating or creating two matrices with the values that we discussed in the lecture, and then you have to deal with the boundaries for both the new and the old time step, which is fine. It's a little bit more complicated. Like I said, it's the text, or sorry, the actual code might look daunting, but it's nothing that you should really worry about. Now, the interesting thing about Craig Nicholson is that you actually, when you have a large time step for Craig Nicholson, you can get these oscillations near the boundaries. And so, let me show you. So even though this method is implicit and it's stable, you're not going to run off to infinite values. This method is susceptible to you ending up with some oscillations. And let me also run this next cell too while we're talking about the Craig Nicholson result, because this one takes a while to run. The 2D one. So let me run this really quick, and while we discuss the Craig Nicholson result. So look at this Craig Nicholson, right? So for this really large time step, you get these oscillations that are actually persistent throughout time. They don't go away. They go away slowly over time. Eventually they would settle down. But you can see for this, I think it's dt. Yeah, dt equals 10, which is quite large. You end up with these oscillations near the boundaries. So it doesn't affect the solution near the center very, very badly, and it's not unstable, but you're still getting obviously a non-physical, if you were solving some sort of physics equation here, non-physical behavior on the side, right? The bar is not going to have oscillations like that. We can look at what that looks like on the sort of static case here as well. Time, flow check, time. I must have defined time in the next thing. Let me see. I think I'm just going to get rid of these lines. I don't need them right now. Let's do that. There you go. So now you can see like what the static plots in each time step look like, and it is indeed affecting the time, the distribution of temperatures even near the center for really early times. So it's important to be aware of that with Craig Nicholson, even though it's a stable method. Okay. So now let's look down here at the 2D case, right? So here you can see this is like that problem that we discussed where you have an enforced derivative of equal to 0 at all the sort of top, right, and bottom boundaries, but then you have a Dirichlet boundary condition on the left. So you can see at t equals 0 you have some the value held at a sharp 1 on the left hand side, and then that intensity diffuses out into the domain, and a quick animation of that looks like this. Okay, so you can see how this high intensity on the left hand side for the first time step really diffuses out very quickly, and you can see how it's the higher intensity is diffusing out into the domain to the right and upwards. Okay, so hopefully that was interesting. I think this is a bit of a longer lecture compared to most, but in any event, it's because we really went over like 3 new methods today. So next time, let's see. I think next time we will be talking about maybe implicit higher dimensional problems, and then maybe getting into elliptic problems when you have steady state style problems. So you can look forward to that. Otherwise, if you have any questions, please reach out. And thank you for listening, and I'll see you all next time.